Hi, this is Barrett Givens, and in this video, we're going to talk about three different possible bases for topologies on R2. So by R2, I mean the plane, okay? And we're going to sort of not use maybe normal terminology. When capital X is R2, we're going to use little x just to mean an ordered pair x1, x2. So when I say an x and I'm in this space R2, x sort of stands for both the quote x and y coordinate, okay? It's x is x1, x2. If I say y, I mean y1, y2. And before we get into the topologies, I want to remind you of the distance formula that you might have learned when you were younger. So if you have 2 points, P and Q, and just like with the other notation, P will mean the ordered pair P1, comma P2, and Q will mean the ordered pair Q1, comma Q2, the distance formula, distance from P to Q, is the square root of Q1 minus P1 quantity squared plus Q2 minus P2 quantity squared. Okay, so that's the distance formula. And hopefully you remember that. Or if you think about it, you can realize that it's actually just the Pythagorean theorem kind of in disguise. Q1 minus P1 is the horizontal distance on that little triangle, and Q2 minus P2 is the vertical distance on that little triangle. And so the distance on the hypotenuse is the square root of the sum of the squares. All right, so that was just a little review that we needed to do. Okay, so there's three shapes that I'd like us to think about. The first one is the open ball of radius epsilon centered at x. So this is a definition that we should know. So the open ball of radius epsilon centered at x, and remember now that x is x1, x2. So x is an ordered pair. And I'm going to write this as capital B of x comma epsilon. So the first coordinate in this capital B notation is the point, is the center, and then the second coordinate is the radius of the ball. So this is the set of all, let's say P, such that the distance from P to X is less than epsilon. So it's looking at all points P whose distance from this special X point is less than epsilon. So like if X is here, you can go out epsilon units. Let's say that's distance epsilon. So we can go out epsilon units in all directions. So if we look at all points of distance epsilon from X, it's going to be all points that are inside this circle. All points inside this circle. And should the edge be dotted or solid? Well, I already drew it, so that kind of tells you the answer, but why is it dotted? If we wanted to include the edge, we would include points that were distance equal to epsilon away. So if I'd said less than or equal to epsilon, it would be a solid edge. But because it's strictly less than epsilon, then it's a dotted edge. So like if I take a point P in here, this distance, the distance all the way from X out to the edge of the circle is epsilon. So this distance D from P to X is, you can see that it's less than epsilon. Okay, so the open ball of radius epsilon centered at X refers to this sort of circle of radius epsilon centered at X. Okay, think of it like a pancake. Okay, a pancake without the edge part of the pancake. All right, and I claim that the collection of all open balls forms a basis. So all open balls centered at all possible points. All right. The second shape that we're going to look at is something that I'm going to call the open rectangle. The open rectangle. So an open rectangle looks like A1, A2. Oh, that's bad notation. I'm going to write it this way. I'm going to say A1, B1 cross A2, B2. So this is confusing because it looks like an ordered pair, like the point A1, B1, but it's not, it's the open interval. So this is an open interval on the horizontal axis. and this is an open interval on the vertical axis. So what do I mean by that Cartesian product? Well, if I take my R2, looks sort of like this. I'm going to look at an A1, B1, an open interval on that axis, and then an A2, B2, an open interval on that axis. And then I'll take the cross product of both of those. So that's all points that the first coordinate falls within this interval, and the second coordinate falls within the vertical interval. So it's like if I take a point X right there, what I can say is that X1 is between A1 and B1, and X2 is between A2 and B2. So here's my X1, here's my X2. So the open rectangle is all of the points that are the first coordinate is between A1 and B1, and the second coordinate is between A2 and B2. So here's my open rectangle right here. All right, I slightly missed. And I claim that these sets also form a basis, okay? The collection of open ball or open rectangles forms a basis. So to check that, you'd have to think about the two parts of the definition of a basis. All right, and then the third shape that I want to talk about is the open diamond. So the open diamond. So an open diamond and I'm going to say of radius epsilon is, all right, d x epsilon. It'll be the set of all p such that the absolute value of p1 minus x1 plus the absolute value of p2 minus x2 is less than epsilon. Okay, so this is kind of like the open ball. It's just sort of like a different definition of distance. I think that this one's going to be a lot easier if I just show you the picture of what it looks like. Okay, so if I take a point X like this, it's going to be all points that if I go epsilon in sort of the north, south, east, and west direction, that lie somewhere in this diamond. So this is the open ball, or sorry, the open diamond of radius epsilon centered at X. Okay. And I claim that these also form a basis. Collection of open diamonds forms a basis. All right. So we have these three possible shapes. We have the open balls, which are like circles in R2. We have the open rectangles, and then we have the open diamonds. And I claim that any one of these collections could form a basis. Let's just think about one of them, maybe just verbally. Let's just talk about it. Let's look at, for example, the collection of open diamonds. Okay, let's look at the collection of open diamonds. So first of all, part of the definition of a basis is that every point needs to be inside one of these diamonds. So if I take some random point over here, is it inside of a diamond? Sure, just pick some number epsilon, pick epsilon equal to like 1/2 or something, pick some number epsilon and like draw the diamond around it. There you go. So every point is inside one of these diamonds. All right, now take two of these diamonds and imagine two of these diamonds intersecting with each other. So let's say I have a point here with a diamond around it. And then I have another point here with a diamond around it. Okay, boy, I'm terrible at drawing diamonds. Okay, and then I want to look at the intersection. I'm going to just erase this radius here because it's confusing me. Okay, I want to look at the intersection and I want to take a point in the intersection. Let's take this point in this intersection. Take this point right here. Is there a diamond around that point that is inside that intersection? Just intuitively, do you think you could draw a diamond around that point? Okay, not worrying about formulas or anything right now, but just thinking about, could I draw a diamond inside of that point? I feel like I could go sort of like up, right, left, and down. I could look at the distances to each of the edges and all of those and just take whatever's the smallest of all of those distances. And then I could just draw a little diamond at whatever is the smallest of those distances. Okay, so I believe that inside the intersection of any two diamonds, if you take a point, you can draw an even smaller diamond. Like if my point was really close to that edge right here, my diamond would have to be really teeny tiny, but I could still do it. Okay, so that's not like a very formal proof, but that's the idea of what you want to think about when you're trying to decide whether or not a certain collection forms a basis. All right, so these are three different possible bases for a topology on R2. In a later video, we're going to talk about what topology is generated by each one of these three, like what is the topology that you get. But for now, I just wanted to define these three terms. All right, thank you for listening.